So the HL portion of the carbohydrate topic mainly has to do with stereoisomerism, the different ways in which things are oriented within carbohydrates. So first of all, the straight chain versions of the monosaccharides all have chiral carbon atoms in them, so they're all chiral molecules, and many of them have multiple chiral carbon atoms inside of them. So like D-glucose, for example, actually has 1, 2, 3, 4 chiral carbon atoms inside of it, as does this is supposed. Oh, sorry. I thought it was on a different page. Fructose also has multiple chiral carbons, but fructose actually only has 1, 2, 3. Sorry, skip back and remember where I am. Now, the way that we're going to name and distinguish different straight chain isomers has to do with the system that they've come up with. Is they look at the carbon atom that is furthest away from the aldehyde group, or the rest of this molecule, which they sometimes call the glyceraldehyde group, because it's kind of like a glycerol 3-carbon backbone with an aldehyde off of it. So we're looking at this carbon atom in particular, and this is what distinguishes L from D. So we're looking at this carbon that is the furthest from the carbonyl atom. And all that's different about D and L-glucose is the orientation of the OH group versus the, on this one, it's the orientation of the OH group. On this one, it's oriented to the right, versus this one, it's oriented to the left. That is the only difference between these molecules, and yet that makes them have different properties. And so the one that's oriented to the right is called D-glucose, and the one that's oriented to the left is called L-glucose. And it turns out that the D form is way more common in nature. It's also sometimes called dextrose because of that D. Instead of calling it glucose, they call it just dextrose. L-glucose is pretty rare in nature and would still taste sweet to your taste buds, but won't be used the same way by your body. So D-glucose is the more common isomer, and it's only based on this hydroxyl group on the carbon that is farthest from the aldehyde functional group. Wow, I'm going to learn how to talk before the end of this video, I think. Now, the other types of isomers to know about are the alpha versus beta isomers. When the straight chain glucose gets into an aqueous solution and it forms a ring with itself, it's actually because of this OH group, that all-important OH group that we just talked about, reacting with the carbonyl group, the carbon in the carbonyl group. So this oxygen that is in the red circle is going to become the oxygen in the ring of the molecule. And so the hydroxyl group swings around, but when it does so, so as a result of if the OH group attacks from the top or from the bottom, that's going to push this oxygen from the carbonyl group either down or up accordingly. So when the attack comes from the top, it pushes the oxygen down, and that oxygen turns into a hydroxyl group that could either be pointed down or that could be pointed up. And so the distinction between an alpha glucose ring and a beta glucose ring is simply whether or not this hydroxyl group on the number 1 carbon is pointed down or pointed up. In an alpha glucose, it's always pointed down, and in beta glucose, it's always pointed up. So that's the distinction between alpha and beta glucose. So the ones given in the data booklet for both fructose and for glucose are the alpha versions, and you can see that on this number 1 carbon, the OH is pointed down, and that's what makes it alpha. So to draw beta, you simply need to flip this H and OH. Everything else about the molecule stays the same. And in fructose, it's the same thing. This hydroxyl is pointed down, the one on the number 2 carbon in this case, and that's why that's alpha. So beta would be pointed up. So those two things would just be swapped. So that's one bit of stereoisomerism to know about for HL. In HL, you also need to know a bit more detail about how starch, glycogen, and cellulose are different, and in terms of their the types of linkages that they make. So we talked about in the SL video about how maltose can link together. When maltose links together, it forms a glycosidic link that we can call a 1,4 glycosidic link because it connects the number 1 carbon on this glucose to the number 4 carbon on the next glucose. So if we're going to draw, did that work? It's up here. Let's undo that. Can we do it again? And there we go. So if we're going to draw another one, it would simply continue this chain. So I didn't really leave myself room for 3, but it would then continue the chain here. There'd be another glycosidic link to the next glucose ring. This OH is now gone, having undergone condensation. And so when you form starch, you can think of it as number 1 to number 4 linkages, glycosidic links between alpha glucoses, all in sort of a straight line. In glycogen, you don't just form those 1 to 6 links, or sorry, 1 to 4 links. In addition to that, the number 6 carbon can also form links. So the number 6 carbon is this carbon up here. And so this carbon can then link to the next one, where this OH can do a condensation reaction with an OH group sticking down from a ring. And they can then form, if this is one of the rings up here, that really ugly ring, sorry about that. So these OH groups can come together and hydrolyze and end up forming a glycosidic link here. And if you count the carbon atoms, if this is the number 6 carbon, this is the number 1 carbon, that's a 1 to 6 glycosidic link. So glycogen has all these branches. So this is a rendering of what glycogen looks like. So it's got the chains, the 1 to 4 links, but it also has branches which are called 1 to 6 links. Okay, and then cellulose. Cellulose is actually made of beta glucose, and beta glucose, remember, it points that. So remember, beta glucose has those OH groups that point up on the number 1 carbon. So the only way that the beta glucoses can actually bond together through the glycosidic links is that each beta glucose sort of has to flip. So if you see, this is the number 6 carbon on this one, and here's the 1. This is the number 6 carbon on this one. And so the number 6 carbon keeps on flipping spots. So each ring is sort of upside down from the next one. And that's just the orientation that they have to take so that they can form these glycosidic links together. So there's still 1 to 4 links. That's still the 4th carbon. And this is the number 1 carbon over here. So they're 1 to 4, but they're beta 1,4 glycosidic links. Now, what that does is as they zigzag back and forth, it actually allows them to form a much more linear arrangement of rings, of beta glucose rings. So cellulose has these super long linear strands of beta glucose rings, and then in between those rings, you've got all these OH groups and you've got all these oxygens which can form lots of hydrogen bonds with one another, thousands and thousands and thousands of hydrogen bonds holding these different strands together. And so all these parallel strands, hydrogen bonded together, create what we call microfibrils. And that gives all that extra strength and toughness to plants. So what you have to be able to do is distinguish between starch, glycogen, and cellulose. The key differences here is that, starch and glycogen both have alpha glucose. But in starch, you're going to only be responsible for understanding that it's mainly straight chain, and it's 1,4 glycosidic links. In glycogen, you've got alpha glucose, you've got branched structure with 1,4 and 1,6 glycosidic links. And finally, you've got beta glucose, which is in long linear strands with hydrogen bonding between strands. We can't digest the cellulose. We lack the enzyme for it. We lack cellulase, but amylase can break down the content of starch, and our bodies contain enzymes that can break off glucose units from the glycogen. So differences have to do with how straight the chains are, the types of links that they have. So these are beta 1,4 glycosidic links. And then some of their properties, like starch being slightly soluble, slightly water soluble, glycogen being insoluble, and cellulose being highly insoluble and very tough.